All right. So, well, first, thank you for this very, very nice conference. So, what I would like to do today is, of course, telling you about work that I've been doing with several people about the statistical physics approach to species-rich ecosystem. But the aim of this talk is also, what will also ask me Jean-Philippe, to try to develop a connection between ideas and methods that have been developed indeed to understand problems in theoretical ecology and statistical physics to something that can be interesting in economics. So actually, we used to have before COVID an eco group meeting, meaning economy and ecology meeting with Jean-Philippe, that then will die out with the COVID. All right, so well, I think Daniel did already a very nice introduction, so I will be very brief. A problem in understanding the dynamics of ecosystem is something that has a long history and received a lot of attention recently because, there are a lot of, there are, let's say, theoretical, traditional ecosystem, but there are also, let's say, what I would call modern ecosystems, so problems that come in the realm of ecology, which are related to actually also to biology, in particular ecosystem formed by bacteria. So now it's a particularly interesting time to try to do theory on ecosystem because there are really not a lot of new data. So thanks to the boom of DNA sequencing technologies, now you can have the relative species, for example, in many ecosystems. So here it's the gap in different subjects. Different columns correspond to different species. So you can study quantitatively many interesting properties. You can also have time dependence. So, it's an interesting times in which you can try to develop theory and then you can try to test them. It's not, let's say, fantastic yet, in the sense that it's still hard to have controlled experiment in the lab, but they are coming, controlled experiments with several different species. So just quickly, the state of the art of the, I would say, in theoretical ecology, and again, Daniel already told you about several different things. So there are some empirical regularities. So for example, the abundance distribution has some kind of power law behavior with then a cutoff at large abundances. This is something that you see in many ecosystems. And so this is something that one should try to explain. Now, the thing is that, I don't know whether it's fortunately or unfortunately, there are several alternative phenomenological explanations in the literature, and actually that are based on drastically different assumptions, more or less orthogonal assumptions. Some explain these regularities based on theory in which there is no interactions at all, and others explain with theories in which there are interactions, and both explanations work equally well to describe these empirical regularities. So it means that one has to try to go beyond and try to maybe, based on the theory, try to find new ways to test and probe the ecosystem in order to advance. Then there is, I would say also there are a lot of theoretical work on models of dynamics of few species, or sometimes there are work that have been done in the theoretical ecology literature on communities as a whole, a little bit like I think in economy, in which you replace the very complicated problem by a representative agent. Here you can have a quote-unquote representative species, but this put under the rug, actually, all the dynamics and the interaction between species. So I would say that, what is interesting for a theoretician, indeed, studying the dynamics of many interacting species and try to develop theories able to bridge the gap between models and data, which means also using the theory to try to ask new questions about the data, maybe new experiments, and then feedback on the theory. So this is the reason about the statistical physical analysis of species-rich ecosystem that Daniel already told you about. So what I would like to do is actually to show you today different behavior that you can find when you study model of species-rich ecosystem in which the model is based on the generalized Lotka-Volterra equation. So again, Daniel discussed it already. So in generalized Lotka-Volterra equation, you have an Ni, which is the abundance of species I. It's a continuous variable. It's an approximation, of course. In reality, it should be a discrete variable. It's positive. S will be the number of species. You have part of the equation, which is just a species that doesn't interact with all the other. Here it's a logistic growth. And then, so it's in equilibrium here, we have Ni, which is equal to Ki. And then you have interaction with the other species. And then if you want, you can add actually two other terms. This is the immigration that Daniel described already. So you see that in this equation, if you put Ni equal to 0, this goes away, this goes away. So if the species is extinct, it remains extinct. But if you put this term L lambda I, then you can have immigration, so the species can come back. And then you have a term here, which is a caricature of demographic noise, so the noise that you have when Ni is discrete and you have birth and death. That here we will take, it's really a simplification. It's white noise, and it's multiplied by a square root of Ni. Okay, these equations are one of the equations that are really well studied in theoretical ecology, and there are others with resources. So what we are going today is try to, again, to see what are the kind of general behavior that one can find from this equation when you have many, many species interacting together. So before actually going into the results, I would like to say that, why I think this is interesting beyond theoretical ecology is that this kind of equation appears in many other different contexts. In fact, I think, of course, I'm not an expert, but I think, for example, prey-predator-Lotka-Volterra equation appeared in economics. I think it's from the work of Goodwin in '64, or maybe even before. I saw something actually on the internet. There will be an Italian that maybe did it before, but okay, maybe I'm biased since I'm Italian. Okay, so in economics, this generalization of this kind of equation appear to study instabilities of large economies. So there is a work of Jean-Philippe, and then there will be also a book that is coming based on Jean-Philippe's lecture about the dynamics of financial markets in which these kind of equations are used. And then again, variance of this equation has been studied in a problem to study recurrent neural network in neuroscience. So here is just one important reference out of others. It was actually very interesting to understand why recurrent neural networks can have chaotic behavior, so some kind of endogenous dynamics. And then also in biology, let's say in game theory with multiple agents, this, again, variation of this equation has been studied. So just to say that, well, variation of this equation appear in many different contexts, so it's interesting to understand what are the different behavior that you can find from those. All right, so let me go back to this equation. In practice, you could say, okay, given this equation, what is Ri, what is Ki, and especially what are the alpha ij? So in practice, only very partial information is known about these parameters. If you know the mean, you are already lucky, and then maybe the variance. It's difficult in as many species case to know this alpha ij. This is an experimental problem. It's really a challenge. People are trying to work on that. For the moment, not much information is known. And also, which is what I was saying here. So, well, it's believed that in many cases, this actually vary quite a lot, as Daniel was already saying. So the model that we, yes?
S, the number of species, you want to think of it as very large?
Yes, we will consider a case in which S is large, because in many practical cases, yes, indeed, S can be quite large, not like the number of particles in physics, but still, quite large. And I will tell you also that the things that I'm showing to you, you can do a numerical simulation and you can see what does it mean S large, in the sense when I can consider S equal to infinity. In practice, if you take S equal to, 40 or 50, you are already in a limit in which all the results obtained for S very, very large are representative of the behavior we find. Okay, so these are the equations. So what we are going to do is we are going to proceed with we're going to study a model which you can think it's either a null model or a model which is replace the complex behavior in the interaction, alpha ij, by a random behavior. So this is something that was actually pioneered in ecology by Bob May, and in physics, as you know, by Wigner, replacing something which is very complex by something which is random. And of course, you shouldn't think that this is the correct model. This is just, as Daniel was saying, it's a caricature, but you can learn many things actually from this, and then you should try to go beyond. So so the alpha ij that we're going to take, so our A and Ka I'm going to take equal to 1. It's just a simplification for this, for what I'm going to tell you, but you can take them fluctuating. But alpha ij, so we're going to take IID random variables, And the important thing is that they have a first and second moment, and the first moment will be equal to mu over s. We take this scaling when s is large, because in this way we have a good limit. And then we have a certain covariance, which is sigma squared divided by s. So sigma will be a measure of the heterogeneity of the interaction. And then it's important to, it's not a physical system, so alpha j is not in principle equal to alpha ji. It's not a symmetric matrix, alpha j. You can have an asymmetry, and the way to measure the asymmetry is this one. So the C means the connected correlation function. So covariance of alpha ji is equal to gamma alpha ji squared. And if gamma is equal to 1, is the symmetric case. If gamma can be between 1 and minus 1. And what Daniel was discussing in his talk at a certain point was gamma equal to minus 1. So this...
Yeah, near minus.
Close to minus 1, yes. Okay, so this is the model. And the idea is to, well, let's try to study what the dynamics of this model when you vary mu, when you vary sigma, when you vary gamma, what are the what is the dynamics and the behavior of this model. Okay, the methods that we've used, and I will not discuss them actually. There is the replica method in the case of symmetric interaction. And then there's dynamical mean-field theory for asymmetric interaction, which I think is actually a very interesting method in this context, because it can shed light actually on different alternative approaches that has been used in theoretical ecology, and I will come back to this in the conclusion. All right, so now with the spirit of this conference, which is more is different, I would like to tell you what are the phenomena, what are the behavior that we find really here, because we look at a very large number of species. And also that we think that some of these behavior are actually more, let's say, I wouldn't say universal, but I would say robust, in the sense that if you change the equation, the Lotka-Volterra, you use something which is slightly different. I mean, this kind of behavior are robust. They are not going to change. They are not really exactly specific to the very specific form of the Lotka-Volterra equation. And again, what collective behavior, it's another way to say phases for physicists, maybe. And what I mean here is really, again, it's important to have a large S, because like in physics, if you have 3 particles, there is no difference. 3 interacting particles, you cannot say that they form a liquid or a gas of a crystal. But if you have, I don't know, 100 particles, and if you do a simulation, you will see different behaviors. And here is the same. If S is large enough, okay, 30, for example, then you really start to see, depending on the parameter of the model, really different behavior in different regimes. And these are the things that I want to discuss now. Okay, so I start with a very simple case for, at least for, I think, well, simple. I mean, it's a case in which you can have an intuition, maybe a more easy intuition if you are a physicist and you work in this order system. So if you take gamma equal to 1, which is a very special case, in which symmetric interaction, then in the case of symmetric interaction, it exists an energy function. So you can rephrase the Lotka-Volterra dynamics as a generalized Langevin equation with an energy function. So there is an energy function, or a Lyapunov function. This is the form of the energy function, and while this is the form of the generalized Langevin equation. Now, if you don't have any migration and you don't have any noise, which is, let me go back, is it's a usual case studied in the case of Lotka-Volterra, so you just put this to 0. Then you can study, well, what you see is that what you are going to study the zero temperature dynamics, or the zero temperature, yes, dynamics after a quench, so starting from an initial condition which is random, for a physical system with this energy. So in order to try to understand what are the different behavior, you can study this energy function, and you realize that depending on the value of sigma and mu, so mu, I remember, is is related to the average value of the interaction, and sigma to the fluctuation or to the heterogeneity. So you find a phase diagram, in the sense that in this regime, when you start from random initial condition, the system goes to one equilibrium, which is unique. So if you start from different initial condition, as long as the and I are all positive, you always go to the same equilibrium. These are trajectory for the different species. And now here you have a region in which you have many, many different equilibria, and I will discuss more, but you can understand from the physics, this is a region in which the system is a spin glass, so there's been already discussion about spin glasses, in which actually the energy landscape is very, very complicated, and you have many different minima, and which corresponds to many different equilibria for the system. And then here you have a regime which is called unbounded growth, in which actually some species diverge, the abundance of some species diverge in finite time.
Basically, the model goes wrong there. The model goes wrong there.
Yes, indeed. It's, we'll say, unphysical or unecological. It's, yes, one should, it's pathological in this regime. Okay, so this is what happens in the symmetric case. So you see, you really have, depending of the value of sigma mu, you have an entire region in which the behavior is different, but it's, I mean, here is the same. It's always unique equilibrium. Here is the same. You have multiple equilibria. So we have considered with Ada Altieri, who is here, generalization of this Lotka-Volterra equation. For example, I told you I put to 0 the demographic noise. You can ask, okay, what about if you add demographic noise and immigration? Then, well, what you can find, I will not go through, but what you find a generalized phase diagram in which, again, it's interesting. You have different phases, and there is a phase which corresponds to a unique equilibrium, except that now, because you have demographic noise, there is dynamics, so it means there is a unique stationary state, and then there are regions in which you have multiple stationary states of the dynamics. And you can also study what happens instead of having this logistic growth, you have another kind of growth, which is related to what is called the Ali effect. So I don't want to go through in detail through this, but it's just to tell you that, I mean, this idea that you have phase diagram and different collective behavior depending on the parameter of the model from this Lotka-Volterra equation is clearly what happens when we study these cases. Yes?
I'm surprised by the Gardner phase.
Why?
Because you have a quadratic, it's like a P=2 spin glass.
Yeah, but there is the Ni, which has to be always positive. So this changed the. It's not Ni is not free, so it's not like a spherical spin. It's which would. In the scale, you don't have a Gardner phase, yes. But here, the Ni are not like spins, so yeah, we can I can give you an intuition later. So all this was for symmetric interaction, and of course, you should say, okay, in general, there are non-symmetric interaction. So what about if you have non-symmetric interaction? So if gamma is between -1 and 1, well, again, you find a phase diagram which is very similar. So you always have this unique equilibrium region. And then you have a region in which you have multiple equilibria. Again, we are studying the case without immigration and without demographic noise. You can compute actually the number of equilibria that you have here. And I think this is interesting for model of maybe of economics and was alluded to already by Francesco. So in this equation, Lotka-Volterra equation, just increasing sigma, which is the heterogeneity in the interaction, you go from a regime with one equilibrium to a regime which has really a very large number of equilibria, which are exponential in S. So already if you have S equal to, if you have 100 species, you have the order of exponential of 100
this is still
equilibria.
gamma equals 1?
No, this is gamma between, well, this is gamma equals 0 actually. So I didn't say that they are stable. I just saying just that there are many, many of them.
So
and that
0 is completely asymmetric.
no, it's
Alpha ij and alpha j are
independent. Yeah, not yes. So in this case, one can study using a method which is called Katz-Rice, the number of equilibria, and indeed, actually, there is a paper by Gerard, not on this model, but on a related model also, in which they find also a regime with many, many equilibria, which are all unstable. So, well, the message of this first part of the talk is that in this Lotka-Volterra equation, which are kind of high dimension dynamical system in which you have heterogeneity in the interactions, very generally you find different phases, different collective behavior, and you have a regime in which the heterogeneity are not very strong, in which you have a unique equilibrium, which would be maybe the simplest case you can think of. But then you go into a regime which is quite complicated with an exponential number of equilibria that I'm going to discuss now.
Just a clarification, so I think it might not come across the difference between where I was setting up and here. So here, it's, if you do natural scaling, so you don't scale things by the S's, and as you increase the number of species, you always go out of this unique equilibrium. right? And so the basic assumption here from the beginning is that the sort of niche interactions are much stronger than the others.
Yeah.
But as you increase the number of species, that always breaks down, and then you
Yeah.
always get out.
Yeah.
Clear on the scaling.
And so something that is nice. So for some, when I told you at the beginning, which is a nice time to do theory, because there is the hope to do a bridge with experimental data, which is controlled in the lab. So indeed, there is a recent paper by Jeff Gore and collaboration between, I think, Jeff Gore and Mathieu Barbier and Guy Boonin, in which they tried to test indeed this phase diagram, and they seem to find with an experiment on 48 species that indeed you can have this difference behavior when you go from one unique equilibrium state to one in which you have multiple equilibria. And okay, so this is, let's say, the first part of my talk. Now, what I would like to discuss is dynamical behavior. So there are two different questions that I would like to address. Actually, one has been addressed already by Daniel, so I will not discuss it. So what I would like to address is there is this idea in ecology that was put forward by Robert May in this paper: will a large complex ecosystem be stable? And the idea was that if you have a complex ecosystem, just using idea from random matrix theory, he claimed that if it's too big, so too many species, then at a certain point it will become unstable. And this will be a way to limit an intrinsic limit to the diversity. Now, again, this is, I don't think is the end of the story. There are many reasons to think that this is not the limit, what limits the diversity. But I think it's something that, so in what Robert May did, he bypassed completely the dynamics. He just said that on the basis of random matrix theory, he put forward this. But now we have a model that we can study, in which we can study the dynamics, in which we can try to address exactly this question to see whether, there is a problem with the stability of the system. And especially what is interesting is, well, if you are beyond what is called the May bound, then the system should be unstable. But if it's unstable, so what's going to happen with the dynamics? So where it's going to go? It's going to have some chaotic behavior, or it's going to settle down somehow. So these are questions that we can address with these models. And again, there is a nice, I think, parallel with the with discussion in economy, and there is this very nice paper by Jean-Philippe and José Morin about will a large economy be stable, which it's a parallel of this. And hopefully there will be also the follow-up on the dynamics as the same thing that I'm going to discuss now. So if, again, I consider the model, the same model than before, and so with no demographic noise and no immigration, here there is the unique equilibrium phase, and now I'm going to increase to see what happens when you go toward this multiple equilibria phase. And so here is what is called the diversity that Daniel already introduced. The diversity, when you increase sigma, it's going down. And what is interesting is to study the density of eigenvalue of the inverse of the stability matrix. So the stability matrix tells you just if I change, let's say, the carrying capacity of the species J, so if I do a perturbation of species J, how much I'm going to change the abundance of species I in the unique equilibrium. So this gives you a matrix of response, and then you can study the density of eigenvalues of the inverse, and this is just the identity plus alpha star. So alpha is the matrix it's the matrix of interaction. Alpha star is just the matrix of interaction reduced to the species which are not extinct. And what you see is that this is just for the case of symmetric interaction, but there is the similar thing for the case in which interactions are not symmetric. Here what you find is you have a semicircle law, and this semicircle law has a certain width. And what you see is that the more you approach this point, the more the system is becoming, let's say, less and less stable. Here is stable because you have all the eigenvalues which are positive, but the more you go here, the more actually the lowest eigenvalue approaches 0, and when you're here, well, the lowest eigenvalue is, 0 in the limit of very large number of species. And the nice thing is that in this context, this line here is the May bound. So it means really that here the system are at the limit of stability, if we follow what May said. And so the question is now, if I take sigma, which is larger, what's going to happen dynamically to the system? So the system start is unstable, And we know that here we are no more in the unique equilibrium, which we have crossed the May bound. What's going to happen?
Could you say again what the stability matrix is? I missed it.
This isn't actually the stability matrix.
No, this is the inverse of this. So it's the, it's
The inflection matrix is not the stability matrix.
So it depends, we call it, so there are two stability metrics. It's the one which is, so the stability matrix, I mean, the way in which I define it, is the how much the abundance, so you consider the unique equilibrium, and you look at how much the abundance of species J change when you do a perturbation on the carrying capacity of species I. So it's like a response function in physics. Then there is another stability matrix, which is a dynamical stability matrix, which
So this is a gradient. Why would that be symmetric? You look at this matrix and its transpose, you're looking at the singular value, that I'm lost.
what?
This matrix you're describing is like the Jacobian. It's a first derivative.
It's
It's not a Hessian or something.
No, it's not. Well, it's in the symmetric case would be like would be related to a Hessian, because it's the response. So a response function is related to correlation functions, and correlation are inverse of the Hessian. But in the symmetric case here, it's not symmetric. Okay, so let's see what's going to happen in this region. So in this region, and we can study it in different ways. So in the symmetric case, actually the answer was known before in a sense. I mean, not in this model, but it was known from the aging dynamics in spin glasses. So the dynamics become slower and slower, and the system approach equilibria which are marginally stable. Now, what we find is that using dynamical mean field theory, we can show that there is a generalization of this finding in the case of asymmetric interaction, in which the dynamic becomes slower and slower. So here you have the correlation between the configuration of time t and the configuration of time t prime. And here this curve are for different value of t prime as a function of t minus t prime for gamma equals 0. So you see that the system actually is decorrelating from itself in a slower and slower way, the longer is the time. So this is really, it's what is called aging. And here, what I'm showing
There's no migration.
here there is no migration.
So they're fluctuating that more and more wildly up and down.
Exactly, yes. So this is indeed, this is the reason. What happens is that there are some species that are going down, 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 and then the ones which are on top are almost stable, but not really. And then at a certain point, the ones which are down will go up again. They will destabilize, and then other ones, they will go down. But this process will slow down the longer is the time.
And the time is finite, not diverging with n here, the time scale, with s, I'm sorry.
Okay, so in the DMFT analysis, you take s going to infinity first, and then t which going to infinity later. But then in the simulation, S is finite, T is finite, and you find, so here is a result of a simulation. So the gamma equals 0. The spectrum of the response matrix has this kind of form from random matrix theory. And what you see here is that these are different colors correspond to different times. And you see that, again, the system becomes, what you see is that the system at long times becomes marginally stable. So here the real part of the eigenvalues becomes equal to 0 at long time. So it starts unstable, and then it goes more and more stable. Yes?
Sorry, when you say response function, it's response to a peak at time t prime?
No, it's the static one.
Okay, because you could also do it.
Yes, we could also look at this. So I think the nice thing that you find here is that in this regime in which you have multiple equilibria, what you find is the system actually sets in dynamically at the May bound, at the limit of stability. And this is something that has been found in physics in the very different contexts, for example, in the Jamingo sphere. So in this context, what it means is that since the stability, the May bound is related to the diversity, it means that the system starts with many species which are present, and then the dynamics of the system is such that the system, in a certain sense, kills enough number of species to become stable. And then once it's at the limit of stability, this is where the dynamics almost stop.
So you're saying it's like unusual spin glasses and you stop at marginal space?
So yes and no. I mean, yes, it seems similar, but in reality, it's not the aging dynamics that Harge studied already. It's, as Daniel was saying, is really related to the fact that there are some species that have an abundance which comes smaller and smaller and then goes up.
Yeah, so you're attracted by the cycle of some form.
So because actually in this model, so Jorge studied models which are different from this one, but in which you have asymmetry. And typically, if you have asymmetry, you have some chaotic dynamics. And here, in this case, without immigration, I mean, you have some kind of aging which is not exactly the same. But so the nice thing is, so the system, there is an entire region of the parameter space in which the system, let's say, self-organize to be exactly at the limit of stability. So in the diversity, this is a way to set the diversity to a very precise value, which is the value given by the May bound. The other interesting thing is that all this region is very peculiar. So this system is at the limit of stability, so it's what is called in a marginal phase or critical phase, in which if you do a perturbation, I mean, to one species, this can have a very, very big effect to another species. So it's an entire region in which the system is very susceptible to perturbation. And so in principle can have avalanches, shock. These are things that we didn't study, but which would be interesting to study. Clearly, if you start to perturb the system, we expect to see things like this. So this is about this phase in which you have marginal stability, which set in. And now, so there will be something more to say about dynamical behavior, but Daniel already told you about, and I think I wouldn't say more. The only thing is, indeed, there has been already a discussion, I think, from people from economic theory, and I think it's a general discussion in the case of complex systems, how much the dynamics that you see is endogenous or exogenous. So sometimes it's clearly that you have the environment that is going to provide some dynamics, but you can ask how much the dynamics you see is due just to the interaction between the species or the agents that you are considering. And of course, in this context, it's a really non-trivial question in the sense that if you have dynamics, then I mean then you know that you have fluctuation. If you have fluctuation, so some species can go down a lot in the abundances, and if they go down too much, then they go extinct. And if they go extinct, well, there is less noise, less dynamics, and so it's not clear whether you can self-sustain endogenous dynamics. And well, as Daniel told you, is that you have multiple communities coupled together by diffusion, then you can have some self-sustained endogenous fluctuation by a kind of insurance effect. So when some species go really down a lot, then you can have a diffusion from another island that saved the species. So I would like actually to conclude the talk saying something about evolution, but it's an evolution which is, let's say, or selection, but it's at the level of the community, and it's a very, let's say, it's again a caricature model of something that can happen. But what we would like, I want to address is, so we started with random interactions, and then you can think that maybe, well, interactions are not random; they have been shaped by evolution. And what we are going to do is putting in a context of artificial selection of a community. So we are going to select community depending on a function, on a property of the community. So the model is, again, the model that we discussed before. And so in which we have different communities, they have their ecological dynamics, then they mutate. The way in which they mutate is, again, very simplistic. What we do is that we mutate the interaction, the matrix of interaction. So we change slightly. So here the matrix of interaction alpha, we changed slightly with some additional Gaussian term for each one of the alpha ij. And then, well, you have different community, which are slightly different. They have their ecological dynamics. And then at the end, after when they settle in, after the ecological dynamics, we look at the total abundance, or let's say the biomass. And then we select the communities which has the higher biomass. And then we continue. Then we go on with this process. And what we would like to see is that clearly here, there will be an evolution of the interaction matrix between the species, and we would like to see, so the artificial selection for the total abundances, what's going to imply on the evolution dynamics of the interactions. And so, well, to cut a long story short, what you see is that here you start from an interaction matrix which is featureless because it's just random variable, to an interaction matrix. Here we put it, I think it's in order of I think, abundances or maybe carrying capacities. So you see that you start to have some structure in the interaction matrix. What you can see, actually, you can study the, you can look at the eigenvalues. So here it's gamma equals 0 for the eigenvalues. If the matrix was completely random, will be just, all the eigenvalue will be just in the circle. And what you see instead is that there is one eigenvalue that pops out. And this eigenvalue actually has an associated eigenvector, and this eigenvector which is giving this structure. So for all practical purposes, actually the matrix, because of this artificial selection, becomes a matrix which has a part which is, for all practical purposes, just random, like the one we started, and then plus a term, which is a kind of, is a rank 1 perturbation. And the nice thing is that here, I was just saying to Gerard before, there are this BBP transition of the eigenvalue that pops out from the bulk in many different fields, and here it's a case in which you find it in the case of artificial selection of communities. So this is the case in which we are just, so this something that we found for, let's say, the Lotka-Volterra model when we select the total abundances, but actually we also found it if we select other targets, and also if we study models with consumer and resources. So this is a work done by Jules Fraboul, who is here and who is doing the PhD with Silvia De Monte and myself.
So you're enhancing to get the left eigenvector being all ones or something like that? I mean, there's one, some...
Yes, it's related indeed. Since here you could think that this is a scalar product between 1 and n, and then you are enhancing this one. If you put the t here, so another vector, you will, yeah. All right, so I will conclude now. So what I wanted to show you is that from this dynamical system equation, which describe the dynamics of ecosystem, which otherwise you can find in many other different fields, and maybe mutatis mutandis you can find in economy with some changes. You can have very different emergent collective behavior. In particular, you can have this marginal stability of the ecosystem, which is as a general mechanism which set actually the diversity or the number of species exactly at the May bound. And the interesting fact that so you find in this way an emergent marginal phase very naturally. In a certain sense, it's an example of self-organized criticality. I mean, I don't know if it's the good terminology, but I mean the system self-organized to be in this particular phase. Then you have, well, this I didn't discuss. This is what yes, is what Daniel discussed, is the the endogenous dynamics which come from coupled communities, and then the final, which is how much artificial selection actually imprints a structure in the matrix. So if you start, even if you start from a matrix which is random, then the matrix evolve and start to have some structure. So the future perspective that we have is, well, first I think there is test all this kind of results in controlled experiments in the lab. I think this is a very nice direction, and which is becoming possible now. There is another thing is, as I told you at the beginning, there are many different explanations in the literature about these regularities that you find in experiments, like this power law distribution that has been discussed already several times. And I think using this model, you can try to find, make connection between these different explanations. So for example, this power law that you find is well explained by a neutral model in which there is no interaction whatsoever between the species. And then it's explained also by some interaction models with interaction between the species. Actually, using this dynamical mean field theory that I didn't discuss, but the nice thing is that you can find at the end a self-consistent equation of a single species, and which you could think is a kind of the equation, the stochastic equation of a representative species. And now, if you look at this equation, it looks like a complicated version of a neutral theory. And so you can think now that, well, neutral theory actually works not because there are no interaction, but it's just in a kind of effective theory which comes from a system with interactions.
So it's effective, but the dynamics is very different.
Yes, the dynamics is very different. Yes, and actually this also tells you that maybe can give idea on what are the experiments to do to try to show that the dynamics is not coming from neutral theory. So for example, if you study response function, then clearly, I mean, if the system is neutral, if I do something to species I and I look to the dynamics of species J, I will get some prediction, and if I have interaction, I get another prediction. So this, I think, it's another direction which one could go.
This single spin self-consistent dynamics you obtain.
Yes.
The theory predicts heavy tail?
Yes. Yeah. And also what, yes, Daniel was discussing also as heavy tail. So the generalization, and then finally, I think it's, and this is more for this conference, I think it would be nice to try to establish connection and maybe generalize what has been found here in other contexts, in particular in economics. So thank you for your attention. And